Hello guys, welcome to the lecture 27 of machine learning series. When it comes to feature engineering, we have already discussed various techniques. Now let us discuss another new technique in feature engineering, that is encoding of numerical data. Now you may be wondering, what is encoding of numerical data? Okay, so we already know encoding of categorical data. Now what we do in encoding of categorical data, if you have an textual columns, okay, if you have strings in our columns, then we convert them to numbers or vectors, right? But here if we see in encoding of categorical data, in encoding of numerical data, we already have numerical values. Now how can we convert this numerical values? Like how can we encode this numerical values? Okay, and also what is the advantage of encoding this numerical values? Okay, first I'll be telling you the problem and then I'll be telling you various techniques to encode this numerical data. Okay, so if you visit Play Store, okay, basically if we visit Play Store, we'll be seeing various apps, right? Okay, now if we go to different apps, then we'll be seeing under that app, okay, under that app we'll be seeing that download section, okay, like how many downloads are recorded for this app. So we'll be seeing various kind of info as well. So if we see that download section for apps that are updated, okay, apps that are updated in the Play Store just a few minutes ago, we'll be having downloads around let's say 25, 30 or 50 something, okay, something like that. But if we see, okay, if we see like popular apps like Instagram or it may be Facebook or it may be YouTube, we'll be seeing that there will be billions of downloads, okay, there will be some billions of downloads. Now when this kind of data is given to you to make some prediction or something, so handling this data directly, okay, like feeding this data directly to a machine learning model is very much risky, okay, because there is huge scale difference, okay, there is very much huge scale difference, okay, where is 25 and where is like 1 million or 1 billion. So what actually we do is, to handle these kind of scenarios, we'll be encoding, okay, we'll be basically encoding the numerical data. Now how do we encode is, now for very small downloads, what we will be doing, will be just creating an category of 10 plus downloads, okay, and next if we, let's say if we have 100 plus downloads, then we'll be creating a category of 100 plus downloads, and next 1000 plus downloads. So in this way we'll be creating various categories for this, okay, they are also numerical, but we'll be creating the numerical in a categorical manner, okay, we'll be just adjusting the numerical values in the categorical manner, so that the models can understand, models or algorithms can understand them very much easily, okay. So this is actually called encoding of numerical data, okay. So to perform this encoding of numerical data, we basically have two types, okay, we just have two types. First is discretization, okay, this discretization is also called as binning, okay, both are same, discretization or binning. And next, second is binarization, okay. So first we'll be discussing about this discretization in very detail, and next we'll be moving on to binarization, okay. So if you understand this discretization, it's more than enough. This binarization is very much simple, okay, most frequently we apply on our datasets this binarization, so it's very much easy to understand and it's a matter of 1 to 2 minutes, okay. So we need to first carefully understand this discretization, okay. So what we do in discretization is, let's say we have an age column, okay. So in this age I have various values like 5, 15, 25 and 26 and 38, 42 and 65, 78 and I have 108, okay. So in this way I have ages of the various people, okay. Now if you keenly observe all these values, okay, from 5 to 78, all the ages are common, right? Okay, all the ages are common because mostly we know that people live till around 80 years of age or 85 years of age. But if we see, this 108 is an uncommon age, okay. So what we actually call this 108 as outlier, okay, we basically call it as outlier, right? So what we do is, okay, after conversion, okay, after performing discretization, how it gets converted is this 5, okay, 5 is represented in between 0 to 10, okay, we create a bin for age 5, okay. So all the ages in between 0 to 10, okay, comes under this, okay, comes under this category, okay. So next for 15, 10 to 20. Next for 25, 20 to 30. For 26, same 20 to 30 age bin, and next 38, 30 to 40, and next for 42, 40 to 50, and next this doesn't come, this comes under 60 to 70. Okay, this comes under 60 to 70 and 70 to 80, and next 100 to 110. Okay, so in this way we create bins. Okay, this is how we create bins. So this is basically called discretization. Okay, so even in this discretization or by binning, okay, discretization or binning, we basically have various types. Okay, so we'll be discussing about that various types. So first let us see the advantages of creating this bins of discretization. Okay, so the very first advantage is handling outliers. Okay, handling outliers, and second is increasing the area spread. Okay, I'll be explaining about this increase of area spread while I'll be discussing about one of the types of discretization. So first I'll be explaining about handling outliers, how this binning handles outliers. Now let us say for the same ages, okay, for the same ages column, let us say I'm plotting an PDF. Okay, so PDF comes out to be like this, which is basically right skewed. Due to this one data sample, what happened, the data has been right skewed. Now let us say I have performed, okay, let us say I have performed binning, and then let's say this is of age group 0 to 10, 20 to 10 to 20, 20 to 30, 30 to 40, and 40 to 50, 50 to 60, 60 to 70. I have something missing, right? 60 to 70, 70 to 80, 70 to 80, and next I don't have any age groups in the middle, and directly I will be having 100 to 110. Okay, so if you see this 110 is over here, right? This 110 is over here, and then if I plot and PDF over this, you can see this would be my PDF, right? Okay, this is my PDF. Now this 110, okay, this 110 is here and 100 is here, right? Okay, 100, 110, this is an bin. Now a person with age 100 and a person with age 110, okay, a person with age 100 and a person with age 100, sorry, age 100 and age 110 are considered the same. Okay, why they are considered the same? Because they fall under the same bin. Okay, as they fall under the same bin, they are considered the same. So now after, okay, let's say after binarization, okay, after binning, if you see the graph has extended till here, right? Okay, graph has extended till here, means there is very much slight kind of right skew. Okay, very slight kind of right skewness. Now if you see, this is a single bin. Okay, this is a single bin, and we are treating a person with age 100 and person with age 110 as equal. Okay, as they fall under the same bin, they are equal. So what can I say? I can say, as this both are equal, can I move this data point over here? Okay, as they both are equal, I can move this data point over here, right? So this spread gets nullified. Okay, this spread gets nullified, and I'll be only having the graph till here. So in this way I can handle the outliers using this binning technique. Okay, so this is the biggest advantage of binning. Now let us see different types of discretization techniques or binning techniques. So we have different types like unsupervised, supervised, and custom binning. Okay, so in unsupervised we'll be having equal width binning and equal frequency binning and k-means binning. Okay, so for equal width we also call it as uniform, for equal frequency we call it as quantile, and this is k-means binning. And under supervised we'll be having decision tree binning, and this is our custom binning. Okay, like we just design our own binning technique. Okay, so in this video our aim will be to discuss these three types of binning techniques. Okay, we'll be avoiding this decision tree binning because we don't even know how and what decision tree algorithm is. So that is why we'll be discussing these three types. Okay, so now you may have doubt that we also don't know this k-means clustering algorithm, right? Okay, so to understand this third type we need to have an idea of k-means clustering algorithm. So what I'll be doing is I'll be just explaining you the basics of k-means clustering, so that you will be definitely having a good insight of k-means binning as well. Okay, so let's start with different types of binning techniques. Let's start with our very first type of binning technique, that is equal width binning. Okay, so as the name suggests that equal width. Okay, till now what we have discussed is nothing but this equal width binning. Now if you see the previous example of ages of different person, we have created various bins like 0 to 10, and 10 to 20 and 20 to 30, right? Okay, now if you see the maximum value and minimum value of the bin, the difference came out to be 10. Okay, and difference came out to be 10 and difference came out to be 10, right? So this is nothing but equal width. Okay, this is nothing but equal width, and this comes under equal width binning. Now how do we actually create this equal width binning is, now first we pick a column. Okay, we just pick a column. Let's say it's our age column. Okay, now in this age column we have the values from 0 to 100. Okay, the minimum value is 0 and maximum value is 100. Okay, so initially we pick first minimum value and maximum value. Okay, from the entire column we pick just minimum value and maximum value, and then we decide total number of bins. Okay, so then we decide total number of bins. Okay, how many bins we want this entire data set to be divided. Okay, like this entire column to be divided. Now let's say bins I have set it to 10. Okay, I just want 10 bins. Now what we do is maximum value minus minimum value divided by total number of bins. So I'll be getting 10, means based on this 10. Okay, that is, this is called width size. Okay, I want total number of bins and with the size of 10. Okay, I want this width as 10. So how do I determine then? 0 to 10 will be my first bin, and next 10 to 20 will be my second bin, and 20 to 30, 30 to 40, and so on up to go so on it goes up to 90 to 100. So I'll be having 10 different bins, and also the width is nothing but 10. Okay, so in this way I'll be doing equal width binning. Okay, I'll be just performing equal width binning. The advantage with this equal width binning is I'll be able to handle outliers. Okay, I'll be able to handle outliers well. Okay, I'll be just able to handle outliers well, but the value spread doesn't decrease. Okay, the area spread remains the same. Now this is the downside of equal width binning. Now to increase the area spread, that is to increase the value spread, what we do, we implement equal frequency binning. Okay, just to counter that, we implement equal frequency binning. Now in equal frequency binning, if you see the name, it tells us the entire definition, right? Equal frequency means I'll be having in each the bin number of persons or number of population as the same. Okay, we'll be just having number of data samples in each bins the same. So that is nothing but equal frequency binning. Okay, it is also called as, if you see, quantile binning. Okay, it is also called as quantile binning. Now let's say 0 to 5, and next let's say 5 to 15, and next let's say I have been something from 15 to 20. Okay, so let's say in this way I have different bins. Okay, but if you see, the width is not the same. Okay, in equal frequency the width shouldn't be the same. Okay, there is no rule that width should be the same in each of the bin. Okay, so if you see in 0 to 5, let's say I have total number of 5 data points, and let's say in 5 to 15 I have total number of 5 data points, and 15 to 20 I also have total number of 5 data points, means I have 5, 5, 5. Okay, the frequency of 5 in each of these bins. So this is called equal frequency bin. Okay, so the population in each of the bin must be same. Okay, must be same in the entire data set. Okay, so then we call it as equal frequency. Now how do we perform this equal frequency binning is, let's say we have an column. Okay, we just have an column. Okay, here comes the concept of quantiles. Okay, let's say we have entire column and we want to convert it to equal frequency. Okay, so what we actually do is, now let's say we have said 10%. Okay, means in each of this, okay, in each of these bins I need my entire 10% population. Let's say I have 100% population. In my first bin I want 10% population, and in my second bin I want my 10%, and in my third bin I want my 10%, and in my fourth bin I want my 10% population. So let's say first 10%, I want my first 10% in my very first bin, right? So let's say I have got my 10th percentile value from 0 to 9. Okay, while I was traversing from 0 to where I'll be getting my 10th percentile value, so I have stopped at 9. Okay, at 9 I have got my 10th percentile value. Next, from 9 again I'll be keeping on traversing, and then let's say I got around 13. Okay, around 13 I got my 20th percentile. Okay, means in my first I'll be having 10% of the population, and from 9 to 13 I'll be having another 10% population, and next let's say from 13 to 19. Okay, I'll be having my 30th percentile value, and here I'll be having my another 10% of the population. Okay, so this is how equal frequency binning works. Okay, that is why it is also called as quantile binning. Okay, so based on the quantile values we'll be just determining the frequency. Okay, so this is equal frequency, and next we have k-means binning. Okay, this k-means binning is also very much simple, but you need to have a basic idea of k-means clustering algorithm. Okay, so I'll be just giving a basic insight of what actually this algorithm is. So don't like try to overlearn or do something, because it is not much used. Okay, it's not much practically implemented, this k-means binning. So mostly we'll be implementing equal frequency binning. Okay, so where should we actually use this k-means binning? Okay, this k-means binning should be actually used when we have separation of the data. Let's say we have taken the entire data set and we have plotted it on a graph, and we have got this type of separations. Okay, these types of separations. Now for label 1 I have this type of separation, and for label 0 I have this type of separation. So in this way there are clusters. Okay, if there are clusters in the data set, then we can apply this k-means binning. Okay, or else never apply this k-means binning, because accuracy gets much degraded. Okay, so in place of that you can definitely go with equal frequency binning. Okay, so another thing I just forgot, actually I told you, I'll be telling how this equal frequency binning helps in increasing the value spread. Okay, so let us say this is the graph. Okay, let us say this is a graph of the data set. Okay, now I have applied equal frequency binning. Now how bins gets divided? With equal frequency, right? Okay, each bin will be having equal frequency. Okay, each bin will be having some equal frequency in this way. Now when I try to plot for this, okay, for this particular data set, the PDF comes out to be this. Okay, so not accurately, but just you can see that the value spread actually got increased. So this is the advantage with equal frequency binning. Okay, the value spread definitely gets increased. Okay, so now let us come back to our k-means binning. Okay, I have told you that way to actually implement this k-means binning, right? Okay, let's say this is our data set. Now initially what you do is, okay, this is, let's say, my age column. Now initially what you do is you first decide your centroids. Okay, you just decide your centroids. Now let us say I have taken some random centroids, that is C1 is equal to and C2 is equal to 50. Okay, from my entire data set. Okay, from my particular column I need to determine 2 centroids. Okay, so number of centroids, there is some other condition for determining total number of centroids, but just for simplicity purpose, to keep it simple, I'm not explaining that all. Okay, first let us say I have 2 centroids. Okay, so I am just determining random centroids from my entire column, let's say 2 and 50, right? So I'll be just creating a table, let's say distance to C1 and distance to C2. Now we determine the distance between this data point and this particular C1 centroid. Okay, you see how we calculate the distance? X minus C. Okay, modulus. Okay, modulus of X minus C. Okay, X minus C1 for this and X minus C2 for this. Okay, so 2 minus 2 0, and next 2 minus 50 40. Okay, actually minus 48, but modulus is being applied, so 48. Next 4 minus 2 2, 4 minus 50 46. So next 6 minus 2 4, and 6 minus 50 44. So in this way we'll be determining the distances. Okay, now after determining the distances, first we'll be taking our very first data point. Okay, so if you see 2, okay, 2 is closer to centroid C1, but it is farther from centroid C2. Okay, you can see the distance is large and the distance is small over here. So that is why we keep 2 in the C1 cluster. Okay, in the C1 cluster. Okay, next when it comes to 4, same scenario with the 4. Okay, so it comes under C1 cluster. Now if you see 54 is 52 units. Okay, it is basically 52 units far from 21 and C1, and it is 54 units, sorry, it is basically 4 units far from C2. So that is why it comes under C2 cluster. Okay, so this is how we determine clusters. Okay, so these 3 data points are one cluster and these 3 data points are one cluster. Now after this we apply our step 2. Okay, we will be applying our step 2. Now how do we apply this step 2 is, we'll be picking first the data points of C1 cluster and we calculate the centroid of that. Okay, so 2 4 6, 2 plus 4 plus 6 divided by 3. Okay, so this will be our new centroid C1 for the second step, and 50 plus 52 plus 54. Okay, so this will be the C2 cluster, C2 centroid for again further calculation. Okay, for the same further calculation. So you may have a doubt that till when should I repeat this entire process? Until, okay, until let's say we have repeated till 4. Okay, we have repeated till 4 steps, and in our 4th step we have got 2 centroids, and sorry, we have determined the clusters in this way, and in our 3rd step also we have determined the clusters in this way. Now the 3rd step, okay, the clusters we have got in the 3rd step and clusters we have got in the 4th step, if both are same, okay, if both are exactly the same, then we'll be stopping our algorithm. Okay, so this is basically K-means clustering algorithm. So how we perform K-means binning through this clustering algorithm is, now this 2, 4, 6 comes under a single bin, and 50, 52, 54 comes under our second bin. Okay, so in this way we perform binning through K-means clustering. Okay, so always remember, perform this type of clustering like K-means binning when dataset is clustered in this form. Okay, it's just divided in this form. Okay, so next we'll be applying these 3 types of binning techniques on a real world dataset. First, I'm importing necessary libraries, and to make you understand in detail about this binning, I'm using this low diabetes dataset from sklearn, and then train test split, and next K-means discretizer. This K-means discretizer provides us 2 types of binning techniques. First is equal width, and second is equal frequency. Okay, so next I'm importing K-means for K-means binning, and next logistic regression model to measure the accuracy scores of different types of binnings, okay, to see which one is performing the better. Okay, so next accuracy score is my metric. Okay, so next I have divided the data set into like x and y variables. X contains my entire features and y contains my training. Okay, that is, sorry, test target column. Okay, x contains my features and y contains my target column, and you can see this is my x. Okay, it contains of 10 different features. Okay, so next if you see, this is our y. Okay, so basically we have imported our logistic regression model over here, but if you see, the values are not in our range. So what I am doing is, I am just converting the y. Okay, so after performing this, what happens is, this values, okay, these values gets transformed to binary values, that is 0 or 1. Okay, so after that I am splitting my data into training and testing, and I'm just training my logistic regression model, and after that I'm just predicting it. Okay, I got around 74% accuracy. Okay, so this is on just raw data. Okay, on raw data I got around 74% accuracy. Now I am applying K, that is binning. Okay, first technique, that is equal with binning. Okay, you can see I'm just creating my object EW, and this K bins discretizer takes 3 parameters, that is total number of bins. Okay, I have already told you, first you need to determine total number of bins, and then encode ordinal. Okay, that is encode is equal to ordinal type, and then strategy is equal to uniform. Uniform means that's equal with, okay, equal between everything. Okay, so you may have it out that we also need to provide minimum and maximum value, but this K-bins discretizer automatically identifies the minimum and maximum value, and automatically does the entire conversion process for you. Okay, so I'm just fitting train data, and I'm performing transformation on test data. Okay, so next I'm training my logistic regression model on this particular dataset, and I got around same accuracy. Okay, so there is no change in the accuracy for the raw data and for the binning applied binning data as well. Okay, so this may be due to like okay, there may be many possible reasons. Okay, so we are not finding much difference after binning and before binning. So now let us try to apply this equal frequency binning, and we'll be seeing if there is any change. Next I am creating this same object, and next total number of bins are 5, and encode is equal to ordinal, and next strategy is equal to quantile. Okay, previously here we done strategy is equal to uniform, and here a strategy is equal to quantile. Okay, so again fit transform, and just transform, and this is my data. Okay, after transforming, this is my data, you can see that. And next I have trained my model, and I got my accuracy. Okay, it is around 76%. Now accuracy has been increased. Okay, when I apply equal frequency binning, my accuracy has definitely increased. Okay, so next let us try to also compare with K-means binning. Okay, so this is the entire K-means binning, so I won't be explaining you much about this K-means binning now, so because you will be definitely getting confused. So while I will be explaining about K-means clustering algorithm, then we will be understanding this in detail. Okay, so after applying K-means binning, this is my transform dataset, and I'm training on this transform dataset, and you can see this is my accuracy. Okay, 52% accuracy. Okay, the accuracy actually dropped. Okay, why it dropped? Because the dataset is not in the form of clusters. Okay, it's basically not in the form of clusters, so that is why accuracy had dropped. Okay, so the best performance among everything is this equal frequency binning. Okay, equal frequency binning has give us best accuracy score. Okay, so I already told you that equal frequency definitely gives us best accuracy. Okay, there may be a reason due to after applying binning we got 74%, and before applying binning there we got 74%, right? Okay, there may be one basic reason, because this equal width binning is used when we have outliers, right? Okay, so if data doesn't have any outliers, so this equal width binning doesn't show that much effect. Okay, it doesn't show that much effect on the entire data set. So that is why this may be most probable reason for equal accuracy score. Okay, so this is entire binning. So next we will be seeing binarization. Now let us see the second technique to encode the numerical data, that is binarization. Okay, you actually what you do in this binarization is you just take the numerical data and then convert them to zeros or ones. Okay, that is just called binarization. Okay, now this binarization is performed in many cases. I'll be explaining a small example. Now let us say government want to give a pension. Okay, give pension to the people. Now we have an column of age. Okay, so what government actually does is it does separation. Okay, it just need to separate the age people, right? Okay, 60 plus must come under one category, and 60 below must come under another category. So what they do is they transform this age column into zeros and ones. Okay, the persons whose age is 60 gets transformed to 0, and persons whose age is greater than 60 gets transformed to 1. Okay, so in this way you'll be applying it in many scenarios. Okay, this is actually called binarization. Just what you do is you encode in the form of binary values. Okay, just zeros or ones. Okay, so now let us apply binarization on a data set. Yeah, I'm taking the same data set. Okay, I'm just taking the same data set, that is load bias data set, and I'm applying binarization. Okay, from sklearn dot preprocessing import binarizer, and threshold value is equal to 0, means less than 0 values gets converted to zeros, and greater than 0 values gets converted to 1. Okay, so this is my threshold value, and I'm just creating an binarizer object with threshold is equal to threshold, that is 0. Okay, basically 0. Then I'm fitting on my training data and just transforming it on the test data. Okay, so this is my entire transform data. You can see mostly ones and zeros. Now I'm just training a logistic regression model. I got around 76% accuracy. Okay, so this is all about binarization. Okay, I'll be just providing this entire notebook in the description. Okay, in most of the cases, okay, in like in very few cases you'll be having the necessity of this binarization and binning. Okay, so most of the times you don't actually use this binarization and binning. So I need to explain, so that is why I explained you. So in case in future if there is necessary, you can definitely refer to this video. I'll be just putting this notebook in the description, so you can try it on your own dataset as well. Okay, so this is the entire video. Hope you guys like this video. If you like the video, please like, share and subscribe. Thank you.